Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation series, and this time it's for typical interview questions on harmonics. And if you go through this presentation and basically, learn it well, it will help you prepare for any future interview questions that will have topics on harmonics. My good name is John Kweku. I'm O2 and I've been a professional electrical engineer for 31 years and I'm based in the United States of America. Okay, so if you go watch my presentation and if you like it, don't forget to select the like button as you can see over here. Then also don't forget to share it with your friends, and also select the subscribe button in YouTube. Below that is my YouTube channel, and that has many more presentations that will help you to build your career and also have other topics that you can watch to prepare you for your future interview in power systems, electrical engineer. Right. Next slide, a typical interview questions that you might encounter, in power systems as a discipline engineer, uh, design engineer, uh, project engineer, maintenance engineer is what are the industry standards that govern harmonics? Because as a discipline engineer, you're supposed to know the standards, that not just have a knowledge of the equipment, but you should also know the governing standards, at least know some pieces of it and some contents of it, what basically the standards are comprised for. So this is how you answer this question. The standard that governs harmonics is IEEE 519, as you can see over here. Okay, then you basically go further deeper, take a deep dive into it and talk about the contents of IEEE 519. Basically, you can say that IEEE 519 sets the limits for total harmonic distortion. Right? THD means total harmonic distortion limits, and that is based on voltage harmonics, right? At a point of common coupling, right? Okay. Next is total demand distortion, and that talks about the harmonics that is associated with current. Right? Then next is individual harmonic limits, the maximum individual harmonic limits, and that is also associated with voltage. Okay, so then you can talk about basically, table 3 of the standard, telling you the different harmonic limits based on voltage criteria. So between 2.3 to 69 kV, right? The voltage range over here, right? It is telling you that the individual, the maximum, at a point of common coupling, and let me explain what the point of common coupling is, right? If you have a generation source over here, right? You can also have an in-field, another generation source, right? Okay. Then this is the grid, right? The utility, right? Okay. This is the point of common coupling that we are talking about, right? The interface between the generation source and the transmission grid. Right? This is what they call the point of common coupling, right? So what is telling you that the standards says that you should comply as a generation unit, right? You should comply, within these standards, right? That is, if you have 69 kV up to 69 kV over here, this should be your maximum individual harmonics, right? So between that 2.3 to 69, the maximum should be 3%. Then between 69 to 138, it should be 1.5%. Then greater than 138, it should be 1%. Right? This is the individual harmonics based on voltage. Then your total harmonic distortion, THD, right? For voltage range between 2.3 kV to 69 kV should be 5%. And between 69 kV to 138 kV should be 2.5%. And greater than 138 kV should be 1.5%. Okay, so below that is basically the formula that is used to compute the total harmonic distortion percentage-wise in voltage, right? Okay, so as you can see over here is the square of the second harmonic, the square of the third harmonic voltage, the square of the fourth harmonic voltage, the square of the fifth harmonic voltage, etc. up to the highest you can have, up to, let's say, the 50th harmonic over the fundamental times 100. So that gives you that percentage that requirements that they are saying over here. So this is the maximum you can make, right? All the harmonics that you are pushing over here should be, if your maximum voltage is 69 kV, up to 69 kV, this is your maximum you can achieve. If it is greater than that, after you have performed your studies, right, then you need to implement mitigation efforts and means. And an example is installing filters right over here that will help to basically mitigate the harmonics that you are producing towards the grid. Next is the current distortion limits, right? Okay, up to 69 kV. Okay, so that one is based on the short circuit current, right? The short circuit current that you have and your load current, right? Okay, so if you have a load, right, a connected load over here, right? So based on the short circuit current and your load current, if you have a feeder here, okay, so as you can see over here, if the ratio of the short circuit current to your load current is less than 20, this is all the limits in percentage that it is requiring, right? Okay, so below all the way up to the 11th harmonic, right, it is telling you, and if your ratio of your short circuit current over the load current is less than 20, then your percentage wise is 4%. And up from the 11th harmonic to the 17th harmonic is 2%. From the 17th harmonic to the 23rd harmonic, it is 1.5%. From 23rd to 35th is 0.6. Then greater than 35th harmonic is 0.3. Right. Then the total demand distortion is 5%. Then between 20 to 50, this is the criteria that it is telling you for you to meet. Then between 50 and 100, this is the criteria, right? Then 100 to 1000, this is the criteria. Then greater than 1000, this is the criteria, right? Okay, so as you know, TDD is based on current, right? Okay, so similarly, right, I2 squared plus I3, the third harmonic, the second harmonic squared, the third harmonic current, the fourth harmonic, the fifth harmonic, all squared over the load current. Right? That gives you your total demand distortion. So this is the percentages criteria that we're seeing over here. Okay. So over here it gives you the discrete individualized harmonic percentage wise. Okay. Thank you. So this is how you answer the question so beautifully, to get all the points that you need basically, to make you successful during your interview. Next beautiful question that you may be asked is, explain to me what is harmonics. Okay, so this is how you answer it. You say that, okay, in the past, right, okay, most of the loads were linear. Like I'll say that more than 3 decades ago, let's say between 20 to 30 years ago, right, there was not much of proliferation of or penetration of power electronic equipment, right? It's other electronics devices. Okay, so as such, most of the connected loads were basically linear in nature. Even if there were arc variances, there weren't that much, many, weren't that many. Right? Okay, so I would say that during that time, I would say that we were close to about 98% linear load and maybe about 2% non-linear, right? Okay, so the effect of this 2% non-linear mode load was not felt. Its impact on their grade wasn't that much, and other equipment wasn't that much because they weren't emitting enough aggregated harmonics. Okay, but with the advent of power electronics, right? As you know, it's a lot of power electronics, and that is wind farms, HVDC, flexible AC device, AC transmission devices, right? Static fire compensators, STATCOM, static synchronous compensators. All these, devices have and UPS, uninterruptible power supplies, right? Switch mode supplies, right? And other lamps, like the baluster lamps. Right? All these devices emit non-linear, and basically emit a lot of harmonics, based on continuous aggregated emissions. And basically, when they emit that harmonics, right, the current harmonics, right, the current harmonics basically flows through a network that consists of impedance, right? Okay, so you have current and you have impedance. What does it? Then basically you get harmonic voltages. So that is how you get the corresponding harmonic voltage, right? Okay, so the output current based on the nonlinear nature of the power electronics basically produces distorted current and voltage. So this is how you answer that question beautifully. And the next slide I'll show you sketches of what is a pure clean sinusoidal wave and distorted wave. So then you can go ahead and do some sketch. You can sketch. Because they say the pictures are worth more than 1,000 words. So you go to the board and sketch. So this is you said okay. This is phase A of the pure sinusoidal wave, right? Fundamental frequency. Then phase B basically shows a lagging, right? Phase B lags phase A by 120 degrees, right? Okay, as you can see over here. Then phase C also lags phase B by 120 degrees. So as you can see, it is balanced, right? It is balanced. So the neutral current is close to zero, as you can see over here. So basically, the output basically is very clean. On the other hand, if you have a pure sinusoidal wave, right, then you have harmonics being emitted by these power electronics devices and other devices, programmable logic controllers, has a lot of power electronics. As another example of a device that emits a lot of harmonics. So let's say it is emitting a tripling harmonic, 10 harmonic. So as you can see, you have the sinusoidal wave. Then in addition to that, it is convoluted with this 10 harmonic part, right? So this is phase B, right? And it has the convoluted 10 harmonic. Then phase C, convoluted with 10 harmonics, right? So at the neutral, right, these harmonics, 10 harmonics will add up, called tripling harmonics, right? 10, 6, 9. Those are tripling harmonics, right? So as you can see over here, at the neutral, it adds up, right? So this is what will come out and will cause a lot of effects on other equipment. Next question. List the sources of harmonics. So this is how you answer that question. Beautiful. To get all the score points. Harmonics are produced from power electronics devices. Right? And don't just say power electronics devices. devices. What are the power electronic devices? You need to go much deeper. Take a deep dive into what type of power electronic devices. And the first one is flexible AC transmission devices, right? FACT devices. Flexible AC transmission devices, right? Okay, so basically, the advent of these devices basically to improve the reliability of the transmission network and then ensure the stability of the transmission network. Basically, on the other hand, these devices end up basically producing a lot of harmonics that needs to be mitigated. Okay, so one of the devices is static power compensators, right? Okay, so static power compensator consists of power electronics, basically, that is able to switch the capacitors and the reactors on. Capacitors to basically produce a reactive power that basically ends up improving the voltages. It's a voltage regulating device, and reactors basically to shunt the voltage, reduce the voltage when you have an over voltage condition. But the power electronics devices that control the switching of these ends up producing a lot of harmonics. Next is STATCOM, static synchronous compensators, right? Okay, so they are quite similar to SVC, right? But basically has a lot more of power electronics in it. Next is a thyristor switcher reactors. Next is a high voltage DC converters, right? Okay, so these DC converters has a lot of power electronics. Actually, they call them, because there are so many, they call them valves. Right? Next is wind turbines. The proliferation and penetration of a lot of our wind turbines as we are moving on to more renewables as a way of a global climatic change, meeting basically the goal, as you know, a lot of our renewables, right, and solar farms, solar PVs. Right? All these devices are controlled by power electronics, the controllers, right? So, as such, it emits a lot of harmonics that needs to be mitigated. And the components of these devices are diodes, thyristors, and insulated gate bipolar transistors. Next is variable speed drives, right? Okay, so as you know, we basically employ a lot of our variable speed drives in the industry. Process industry is basically more of optimization of performance of motors. We use a lot of them in the oil and gas industries as a way of optimization of motors that are in the oil and gas industries. Right? But the power electronics that basically operates operates the motors to achieve to vary the speed based on demand, as a voltage over frequency, right? Basically results in the emission of harmonics. Okay, next is soft status, right? Okay, so as you know, to mitigate inrush to motors, right? We use soft status. Okay, so soft status can have a thyristors that basically, it's able to have the motor have a reduction of inrush current, right, and have a smooth torque, gradual ramp of the torque during startup, right? Basically, optimization of performance and basically improving the efficiency of these motors. They utilize a soft status, but the power electronics basically that is used in the soft status emits a lot of harmonics. Next is arc furnace, right? Okay, so arc furnace due to the intermittent loads basically results in a lot of unbalance, right? Okay, so the arc furnace itself also utilizes a lot of power electronics and this results in the emission of harmonics. Next is a ballast lamp. Next is UPS, uninterruptible power supply, right? And that also has a lot of power electronics. Switch mode supplies has a lot of power electronics. Arc welding, the intermittent load causes a lot of unbalanced loads. Then PLCs, controllers, then data centers. All these are the sources of harmonics. Next, Question, beautiful question. Is explain to me how a variable speed drive works and the benefits of a variable speed drive. This is how you answer that question, beautiful. What you have to do is basically go to the board and sketch, give it a sketch, and on basically all the components and what comprises of the variable speed drive. Okay, so this is the input voltage, right? You sketch it, 415, 430 volts, right? Okay. Then how do you achieve that 430 volts and 450 volts that is required by the variable speed drive? There is a step-down transformer, right? Okay, so let's say from 13.8 kV, 34.5 kV, whichever transmission level, distribution level voltage that you have, right? You step the voltage down to a voltage that is required. That will be very good for the variable speed drive as an input voltage. Okay, and the input voltage for this power electronics is very low voltage, 415, 430 volts. So from 34.5 kV to 415 or 430 or 30.8 kV to 415 or 430 volts, that becomes an input to the rectification section. That is a converter, as you can see over here, right? So you have an AC input at a voltage of 415 volts or 430 volts that comes in here, right? That comes, like I told you, I've explained to you the source, where it comes from, where it gets stepped down to a lower voltage that will be adequate, that will be compatible for the variable speed drive. Okay, so this comes in here, and the section, these are diodes, right? Okay, basically that rectifies the AC voltage input to a DC voltage equivalent. So after this side, you have a DC voltage with half cycle difference pulses in the positive, right? But it has some ripples on it, right? The ripples, it has to be smoothed using a filter, a reactor, that basically smooths the surface to achieve a pure DC voltage, right? At the same time, it has a capacitor, right? That stores all the, that has a charge, basically, that gets charged to maintain the DC voltage here. So this section is an inverter, another converter, but it inverts the voltage from DC to an AC equivalent, right? Okay, so as you can see over here, these are excuse me, insulated gate bipolar transformers with transistors, right? As you can see, they are indicated by switches, as you can see over here, right? So utilizing a pulse width modulation switching, you are able to turn on and off all these switches, right? These power electronics switches to achieve quite close to a sinusoidal wave. It goes like this: pulses, right? Pulses, pulses, pulses. So what you are doing is basically creating the sinusoidal wave, right? Same thing, pulses. So you are utilizing these switches to create pulses to mimic the sinusoidal wave to be utilized by this motor. Right. So this is how you use it to control the speed of the motor based on the frequency and the voltage, and they follow this relationship, the voltage over the frequency. And as you vary the frequency, you vary the speed of the motor, and also you vary the demand, right? You are able to control the demand, right? if let's say you have a motor that is coupled to a pump, right? And let's say initially the pump was working at a full load, right? And let's say you want to operate it at half a load, right? Then the speed has to change, right? It has to go to a lower speed, right? Then you utilize basically you change the frequency to achieve that half load. So in effect, you are optimizing the performance and enhancing the life cycle of the motor, right? And improving the efficiency of the motor, utilizing the variable speed drive. Next, you can go ahead and do a sketch of this. Okay, so basically what I showed you is basically the variable speed drive, and that's the controller, right? As you can see it, the previously. And you have an input controller that the operator operates, right? That is going to be the demand, right? This is what I want. This is basically, with a full load, half load, 3/4 load, right? Then based on that, the controller is going to do its job and basically control the speed of the motor based on adjusting the frequency and the voltage. Next is another question, beautiful question. Tell me about the effects of harmonics on equipment. So as all these devices that is full of power electronics emit a lot of harmonics, definitely it's going to have a detrimental effect on other equipment that is in close proximity to these power electronics devices. So we need to take a look at how you answer that question. Okay, so you have the flow of tripling harmonics, right? Third, 6, and 9. We call it tripling harmonics, right? Okay, so these tripling harmonics basically collect at the neutral of any equipment that is wound in a Y configuration, right? Okay, so these basically create a flow out and creates a heat in cables, power transformers, and motors. Next is a power quality issue, right? Problems, right? Okay, because of the voltage and current distortion, right? Okay, so we have a mirroring and protective relays, right? That rely on all these signals, voltage signals, and current signals to make a decision, right? Whether to trip an equipment. But once these measuring signals are distorted, it affects their reliability. And basically, you see that the protective relays are going to operate spuriously, create a nuisance tripping because it is not measuring the true replica voltage and current signal. And also, you see that the mirroring devices are also not going to produce the correct measuring indication of voltage and current in the power system network. Next is hysteresis losses, right? Okay, so as you know, these create variation of harmonic current, right? And that is based on the square of the frequency, right? Okay, so you have a current squared and you have a frequency squared. So that creates a lot of heating. Next is because of the heating that is created in a power transformer, right? Due to the tripling harmonics, right? That means that if you do the studies and you identify that you have an issue with harmonics, right? And you have a power transformer, that means that you need to consider basically upgrading, increasing. Let's say if originally you have a 30 MVA transformer, right? Then you need to consider the K factor due to the harmonics, right? And increase the MVA output to, let's say, 40 MVA or 45. So that itself, increasing the MVA output basically is higher cost due to that. Next is because of the heating, it results in killed capacitor banks, and due to distortion of voltage and current signals are being measured to these capacitor banks. Next is you have fuses and circuit breakers also tripping, right, due to the protected relays not measuring accurate voltage and current. Next is because of tripling harmonics flowing through the neutral, right, it means that you have to oversize the neutral bar. Everything about a neutral has to be oversized to be able to handle that, to prevent heating. Next is a harmonic resonance, and that is very important, right? Okay, so as you have capacitors, right, in inductors, reactors combination, right? Okay, so for instance, power transformers are inductive. Motors also have a winding, they are inductive, right? Okay, transmission lines, inductive, right? You can have also a capacitor bank, right? So the flow of these harmonic currents, right, with the capacitor and the reactors, inductive elements of the power system network, right, it forms a harmonic resonance, which basically amplifies the voltage that can be very disastrous for the installation system of these equipment. Next, tell me about how harmonics can effect can be mitigated, can be minimized. Okay. And this is how you answer that question. First thing you need to do is performing harmonic studies. Okay, so harmonic studies, there are two types that is frequency. You perform network impedance calculations where you model the network's impedance in an admittance matrix, right? Then you perform current injection, right? If you have different buses, right? Different buses, right? What you do is you inject current, harmonic current at different frequencies, right? Then you measure the corresponding voltage. Then you determine the impedance and compare it with the network impedance. Next is a harmonic load flow, right? Okay, so what you do is basically similarly inject harmonic currents and you measure, calculate the harmonic voltages. So that is the first thing you want to do if you have a lot of proliferation of power electronics in your network, to determine the need to mitigate it. Next is how you install filters, right? And you can install tuned filters, right? So what is a tuned filters? Very simple, right? L, R, L, C circuit, right? That's a tuned filter, right? So for the tuned filter, we have a passive and active, right? Okay, so the problem with the passive ones is they drift a lot, and you have to basically tune it. Next is the broadband filters, where we have low pass and high pass filters. Then active filters, basically that utilizes power electronics. Right? So after you have performed your studies, right, you determine the need to install these filters to mitigate these harmonics. Then basically you can decide on based on analysis to install which type of filter you need to install. Next is it's basically uh, increasing the pulse size of your uh, converter, right? Okay, you can change from 6 pulse to 12 pulse to 18 pulse to 24 pulse. So as you increase the number of pulses, right, then basically your harmonic content basically start decreasing. And but the caveat is that translates into higher costs, higher capital costs. So that is one thing that you need to also consider, right? Okay, balance it with do cost benefit analysis with installation of projects. Next is phase shifting transformers, right? Okay, so that itself leads to cancellation of harmonics, right? Okay, so they utilize that even in ATDC, right? Line commutated converters, right? Where you have transformers that are wound Y, Y, delta, and the other one is wound why, you know, so basically you're able to achieve a cancellation of the fifth and the seventh harmonics, right? And that itself helps you to reduce the size of the filter and cost as well, right? Next is installation of reactors, right? Okay, it's able to, the reactor is able to smooth in, you know, remove all those ripples, right? Next slide basically is the last slide, and you know, I'll say that thank you so much for your listening ears, and this is my channel, my YouTube channel, and basically you can basically take a look at it, and it has a lot of you know, resources for you to watch and listen and get yourself prepared for your next interview and be very successful, be very confident to be able to answer the questions you know, beautifully and score all the points on the score sheet. Okay, so if you like my presentation, basically, you know, select the like button, right, as you can see over here on my YouTube channel, right? Then share with your friends, your colleagues, and select the subscribe button. And below that is my YouTube channel, and click on it, and it takes you right there. Right? Thank you so much, and look out for the next presentation. I think the next presentation that I'll put together will be the types of grounding schemes that we have in power systems. Then another presentation for your to prepare you for your next interview and give you a takeover questions will be on protection systems. So in that one, I'll cover, you know, different protection systems in power transformers, generators, and motors. With that, say thank you.